Well, let's get started.
All right, so that sounds great. So let me first, this cluster is actually deployed to AWS. The Community Edition actually supports a number of platforms. We support AWS, vSphere, OpenStack, VMware-based products like Fusion and Workstation, as well as VirtualBox. Just a note of warning, if you are installing our Community Edition on a laptop using a standard laptop-based virtualization solution, your mileage might vary. You should probably have 16 gigs of RAM. There's a number of VMs that need to boot in order for the platform to be fully functional. And we built out those particular providers for test usage, kicking the tires, playing around with it as a dev, but not for long-standing clusters. For long-standing clusters, we recommend AWS, vSphere, or OpenStack, or a traditional cloud platform. And that's where you're going to get the best experience and actually have the most capacity, as most laptops don't have enough resources for large-scale clusters anyways. So this particular cluster, we can go to our cluster view. It has 2 instance managers. That would be the equivalent of a machine that's running Dockerd. We do not use Docker's tooling internally, but that's the closest comparison. It's our instance managers are what are responsible for bringing up and down containers and managing the container lifecycle within our clusters. So we have 2 instance managers in this cluster. We have 18 jobs that are currently running, and then 20 instances of those jobs, because you can say a job should have 2 instances running or 3 instances. So a job is a unique piece of work that needs to be run, and then the instance is how many instances of that work need to be actually running. You can also see that we have this concept of data centers. Within Community Edition, we only support a single data center, as we do not support our full hybrid environments with Community Edition, mainly because of the difficulties automating VPN setup and some of the complexities there. So the data centers are your logical unit for best path routing and optimizations for hybrid environments. This one just has one. And then you can see your standard resource utilization, RAM and disk across the IMs. You can see, what the instance names are, how many job instances are running, as well as the tags that belong to those particular instance managers. In hybrid environments, you can use those tags to schedule to different hybrid clouds, and you have full portability between different environments. This is just platform AWS, but we can also lock things to a particular host and make sure they schedule to a particular host if that's important on a scheduling side. And then let's go take a quick look, and we're going to just breeze through kind of the top level objects, and then we'll dig into a little bit more depth. Okay, great. So the apps are things that a user would deploy. So my Node app, my Python app, what we're looking at here is the Lucid app. That's our web console. That's running inside of the platform, not sidecard, but actually in a container, just running as a normal job. Our Continuum Guide is our inline documentation. We have a full documentation portal built into every cluster, mainly for air-gapped deploys, where you may not have internet access, and you may still need access to documentation. And then you can see that we have a MySQL and Postgres app that are deployed. And those are just traditional containers running MySQL and Postgres. Those also include full persistence, and we do that via NFS right now for those singletons. Now, if we wanted to launch additional applications, we have some very nice flows for doing that. Oops, there's a button in front of me on my screen. So this is kind of our launch Docker image interface. Allows you to very quickly provision common services with Docker. You want to launch an Ubuntu image, you want to launch a Debian image, you want to launch Redis or MySQL or Memcache. These are single-click installs, and I can kind of show you how that works. And we'll just start with Nats because that's one of our homegrown properties.
Yeah.
So
tell us what Nats is.
So Nats is a very simple, easy-to-use messaging system for cloud applications. Okay. So it allows you to send messages via a pub/sub model, broadcast messages, but is very lightweight, designed to be extremely performant in the millions of messages per second, outperforms most other message queues on the market, as it's not really a queue, more relatable to something like 0MQ, where it's more of a messaging, but not persistence, not message replay type of system.
Okay.
So let's go ahead, and we're just going to go ahead and launch this Docker job. We're going to go and we're going to fetch some metadata. We're going to go and download the layers from the Docker repositories, and there we go. We have a launched Nats instance. We can see that it was deployed by me. It allows SSH into it. it is started. I can see what instances are running, what instance manager they're running on, what my start command is for NATs. We can see all the resource utilization as well. It just started, obviously, because we just started this job. But we track all of the network, disk, CPU, et cetera, and give you easy metrics to all of these different pieces.
What would be what are you seeing as the alternative that customers are facing when they go through this process? Is it all on the command line then, essentially?
So there is the web view, and then there's also the command line, and we have first-class support for both. We have what we call the APC client that we ship with our clusters, and we'll be demoing a little bit of that in a little while. I like to start with the web view to kind of go over what's in the system, give a little more transparency as to how the system works, and then we can drop into the command line and kind of show more of the developer experience.
But what have you automated up to this point that previously, a developer may not have had that privilege?
So there's a lot of things that we've automated. So in a lot of traditional systems, you can easily bring up a database like Postgres. So let's look at Kubernetes. I can bring up a Postgres instance in Kubernetes. But it's not going to carve out databases for me. It's not going to adjust grant tables, create users, create sandbox databases by default. And it's not going to do a lot of the operational pieces that you want done with your data service, other than just being able to deploy the data service itself. We actually do full-fledged management of those data services. So I can bring in a Postgres server, but I can also say, hey, system, go make me a database on that Postgres server. Carve me out a username and a password, set up the grant tables, do best practice security on that new sandbox database, and then provide me a database that just works.
Speaks to this time that we're in now. We now have a much better idea of what can be abstracted.
Exactly.
As before, we were just trying things.
This is very true. So as we look at some of these other tabs, scheduling is where the job is running. We have our networking, so we can see what ports are open on our job, what routes, if we've attached any. Since this isn't a web app, I didn't attach any routes, but we might want a TCP route or something at some point. We can also get unified logging. There's not a lot that comes out of NATs when it first starts, but what's nice about this is that we can export those logs to any syslog compatible service. So you want to output all of your cluster logs to Splunk or to Elasticsearch. All of that is possible within the platform. You can see what policies apply to this job. We'll get more into depth about that in a little while. And then you can also see the audit trails for this job. So I created it at 11:46, and I started it right when I created it. But we know every granular action, whether that occurred from me or something in the system, and make sure that the audit trails are very complete for everything that happens within the system. So the next top-level piece is what we call capsules. And capsules are, again, just a container, but they're designed to run operating systems. So if I want to create a capsule, I can create, this is actually probably something better from the command line. So let's go ahead and do that. So let me go ahead and bump up this size. And if we take a look and see what capsules are there, I don't have any. And I'm going to go ahead and create a capsule called Ubuntu. I'm going to use my Ubuntu image, and we're just going to go ahead and create that. It's going to ask me what resources I wanted, and then APC capsule connect Ubuntu. I have what looks like an Ubuntu machine with a lot less services running on it.
Right.
It's running in a container, and one thing that is very different about our model versus the Docker model is that we don't believe that things should have open reign on a network. Network access should be restricted by default. So we go for a full network isolation for every container that we spawn if policy has not opened up network routes.
So how would Docker treat this then?
So right now I'd have full internet access in Docker, and I'd be able to pull whatever I wanted, and I'd be able to connect to anything that was running on that machine and be able to connect to all the different services that I want in an open network.
And you guys believe that?
That's fundamentally flawed. If I'm able to, so say that I have a production environment. Even in my production environment, certain things should only be able to talk to other things. And you want to reduce the blast radius of anything that gets exploited by limiting those network connections. So by closing off all the network by default and understanding the relationships between my containers and opening up the network routes as needed, they only talk to the things they're supposed to talk to that they need to function. And it doesn't allow them to use it as a jumping point to other jobs that may be running in that same networked environment. So for instance, if I try to curl google.com, we can see that I am completely failing. I'm not getting any response back. I have no internet access. I have no DNS. So let's go ahead and exit this capsule. And we're going to update it. And we're going to say for the Ubuntu capsule, we're going to allow egress. So outbound egress. Let's go ahead and open that. So we're going to go and recreate this job. We can connect to this job now. And if I go ahead and curl google.com, we can see that my internet access has been restored. Now, the policies in the system allow you to automate this behavior. Okay. So you can say, yep, by default, they should get these types of network policies, and you can kind of abstract away a lot of these different pieces. We find that this is really important, understanding the relationships between your containers and what they talk to, and making sure that everything is really locked down is critical for the promise of more containers per host and better consolidation of your infrastructure. If you don't have those things isolated and you put more containers on a host, you're actually increasing your risk as anyone that can break into a single application in that host may be able to connect to other data services, etc., and escalate privileges. So, capsule delete. Let's go ahead and get rid of that, and then we can go right back. Got a decent idea of that. Now, obviously, those capsules could be configured with Puppet or Chef or Ansible or any VM provisioning tool or traditional configuration management you have today. You can easily snapshot the capsules after they've been configured and create packages from them and launch jobs and do all of these workflows that are very familiar to the way people do business right now.
So those capsules are not necessarily sandboxes, or are they?
So those capsules are sandboxed, but they're really used for, I need an interactive way to play around with the operating system. Maybe I want to install a service that's available through apt-get.
So it's not entirely isolated.
So it is. It uses the exact same containerization that we use for all of our other jobs.
Right.
So it is encapsulated, but it's designed as a jumping point to create new pieces. So the idea is I open up this capsule, I do whatever configurations I need, I snapshot it, and then I create a job from that resulting package that I'd run in the system. So it gives you a workflow that makes sense and is more familiar to people that have more VM-based experience in their previous jobs. So now let's take a look at all the jobs, and we'll notice that there's a lot more here than we saw before. So at the top, we can see the standard user-based apps. We can see the NATS application that we deployed. But we also see these semantic pipelines, and we see stagers, and we also see, the gateways were moved. So semantic pipelines are special for us in that we try to lock down services the best we can. And the reality is when a developer joins an organization and they have an important role, they're an architect, they're a senior engineer, they get a lot of access credentials to different services. So they know what the Postgres master, database password is. They know what all these different service passwords are because they need them in order to do their job. But this leads to a lot of problems, is that if human beings know the credentials to these services and they switch jobs, it leads to password rotations being required. It leads to, possibility that those passwords could be compromised, and they're static passwords. So there's a lot of management and security at the enterprise level that goes along with that. And we tried to think of solutions for doing that. And we were like, well, one solution is we never give people real passwords, never give them real logins. So we built these semantic pipelines, and they sit between you and your data store. So when your job thinks it's connecting to Postgres, it's actually connecting to one of our semantic pipelines.
It's like a proxy?
It is, but it's a very intelligent proxy in that it actually can give you credentials that are completely fake. So when you go to connect to that database, you get some 20-character username, 20-character password, a database name that doesn't really exist. And when you connect to the semantic pipeline, it's like, yep, that's the one that I was expecting you to give me credentials for. And it knows the real credentials to the data store behind the scenes and rewrites your requests to work with that data store.
How do you know if the pipeline is healthy and if it's actually working the way you want it to work?
Well, network-wise, it is impossible for the job to actually connect to the parent database. There is no network route to the real database. The only thing that has that network route to the real database is the semantic pipeline itself. And you only have access to connect to the semantic pipeline. So if you can connect to the semantic pipeline, to what database URI we gave you, we know for a fact that you can't get anywhere other than the semantic pipeline. So there is also enforcement to guarantee that you're talking to these proxies. And you can have policies and generic service gateways that bypass some of these pieces. But by default, they are enabled for Redis, MySQL, Postgres, and a number of other services.
So what about the management of the pipeline itself?
It's all automated in the platform.
Okay.
You don't even know that it's there. So when you deploy your job and you had a binding,
So you don't need to worry about the health of it necessarily.
No, the health management features that track the health of all of our other containers also track that for the semantic pipelines. We also pair them one-to-one with each job instance to guarantee high throughput.
Okay.
So it's not a single proxied point that would consolidate bandwidth and hurt your speeds on the network.
Okay.
Now I can show you some examples of that in a little bit. And then we also have our stagers, and the stagers are the equivalent of, kind of like build packs from Cloud Foundry or Heroku. Allow you to automate, staging Java and Node, Perl, Python, Ruby applications with APIs available for any other languages that you'd like to stage, as well as open source repositories with sample stagers for a lot of other frameworks. And there's some stagers that are paired with some of our sample apps as well. So now the services tier is where things start getting a little bit more interesting. So unlike systems like Docker and Kubernetes, they're very, very tied to things like environmental variables, right? The problem with environmental variables is that if I do everything based on IP and things move, then I have to rolling restart different things.
Mm-hmm.
So say that I have a data store that I want to move to another location. Well, anything that was referencing or trying to connect to that data store probably had an environmental variable on the container that said, hey, my data store is over here. And they're all going to break until you restart them with the new credentials. We find that this model is very brittle. So instead, basically, you're not tracking the IPs as they relate to an entity in the system. And that makes your infrastructure brittle, makes rolling restarts something that is required for a lot of these different pieces, and doesn't work as well as I would expect. So instead, we actually provide what we call FQNs, which are fully qualified names. We attach those to our workloads. And all of these services and bindings within the system use those FQNs. And that way, we always know what should be talking to each other regardless of IP. And we can go ahead and patch those things in together dynamically for you. Now, the services can include data services like NFS mounts. It could be data services like a Postgres database. It could be a network service that includes a sitter or port range or a host name that you should be allowed to connect to. And there's 3 tiers to our service infrastructure. We have what we call providers, which we'll jump to. And we can see I have 3 providers loaded in the system. I have an NFS provider, I have a MySQL provider, and I have a Postgres provider. And providers are things that you can carve a multi-tenant capable service out of. So our NFS service will allow you to provision an NFS, and we can provision multiple services off of that one NFS mount, NFS location that you've been given. And we can share that for multiple services safely. Or for MySQL, I can carve out a database with specific usernames and passwords and guarantee no one else can connect to that database. So anything that can provision a multi-tenant environment is basically a provider. And then the service is the thing that you want to provide to a job, so a database or a mount. And then we have what we call bindings, which are my app needs this service, so I'm going to bind to this service. So it's this 3-tier system.
Okay.
Now, some services don't make sense from the provider sense. There is no way to do multi-tenancy. Think Memcache.
Right.
It's a single thing. It doesn't allow you users in groups or anything like that. So those are just services, and they don't have a provider. And providers are optional in our system. And so I can create, these services very, very easily. And I can actually show a quick example of that. So APC service create, I'm going to create a Redis service of type Redis. I'm going to go ahead and create it. And that was it. I created a job with Redis in it that I could bind to other jobs, and it's just a singleton. And that job should only be used for one set of jobs or one concern. And that's how easy it is, just as easy as it was with, the Docker flow, but that's actually our Redis service, not just a Docker image running. Now, if I want to create a service for something like a database, it's a little bit different. So we're going to take a look at my provider list. We can see that I have a Postgres provider. Let's go ahead and create a Postgres database. So I'm going to say service create. We're going to do it for the to-do app I'm going to deploy in a little bit. So we're going to just say we're going to create a database called to-do Postgres. And I'm going to use this particular provider for that. I'm going to use my Postgres provider to create this service. Now, it's going to talk to that provider. It's going to say, hey, provider, I need a new database. Can you go create this for me and set up all of the security for it? And then it's going to return me a service object. And now when I do a service list, we can see that I have my Redis service that I had, but I also have my to-do Postgres database that I could bind to a job and is actually been provisioned for me by this provider tier.
Okay.
So now if we go back and we take a look at the different services, at the bottom we should see our to-do Postgres. It was provisioned through my Postgres provider, and everything is tooled the way I would expect. Now, the different service gateways that we currently support are here. So we have a GNATS-D service gateway. We have Memcache, MongoDB, MySQL, the network services, the NFS services, Postgres, RabbitMQ, Redis, and S3.
So what will you be adding?
So this actually uses an API that allows people to add whatever services they want.
Okay.
So we already have a sample of how you could have written our Redis service gateway in Ruby in less than 100 lines of code. So we have these examples. They're very trivial to write. We don't have a lot of new ones on the horizon. We have a couple around AWS-based services. So we just added S3, but we've actually thought about ways that we could auto-provision things like RDS or other services from Amazon.
Okay.
But those are still in flight with not an exact ETA.